Welcome back. We are in Chapter 7, Section 11. This is going to give us a review of some of the theory involved in dealing with binary data. This is actually the last section we're going to talk about in Chapter 7. Originally, I assigned you some readings in the later sections, but upon closer inspection, those sections are really not worth our time. So I think they would only confuse us, so we're just going to ignore them. And after this, we will move into Chapter 10. So you have some readings on Moodle already for Chapter 10. First thing we want to talk about is the Bernoulli distribution. So binary data follow a Bernoulli distribution if each observation is independent, each observation falls into one of two categories, and those categories are failure or success, a 0 or a 1, and the probability of success is constant for each observation. So what does this mean and what doesn't it mean? It does not mean the probability of success and the probability of failure are equal. It means from observation to observation, the probability of success is the same. So an example of this is flipping a coin. Every time you flip a coin, the probability of success is the same, right? So if we say the probability of flipping a coin and it landing heads, that's always 50%. Every time you flip the coin, it's always 50%. In this case, the probability of failure is equal to the probability of success, but that's not what we care about. Also, some quick notes on notation. You might notice that in the first sentence, the y is lowercase, but in the third sentence, it's capitalized. That's intentional. The y in the third sentence is a random variable, and the y in the first sentence is an observation of that random variable. So random variables, while they're still kind of ambiguous, they get capital letters. Once you observe a specific number, that observation is a lowercase letter. And pi is not 3.14. Pi here is a Greek letter pi representing the true probability. So we said that parameters get Greek letters like mu or sigma. This is a parameter pi. So that's the truth. The one that we deal with, the one that we're estimating, is p. So p sub I. Now, thinking about our example in flipping coins. If I'm flipping the coin, each time I check and see if a flip is heads or tails, if it's a 0 or 1, that's Bernoulli. So one single flip, deciding if it's a success or failure, that's Bernoulli. On the other hand, if I flip it 10 times and I want to count the number of times it landed heads, that's binomial. So there is a relationship between the Bernoulli and the binomial. The Bernoulli is a special case of the binomial when n is equal to 1. So it's a single binomial thing. The PMF for the Bernoulli distribution looks a lot like the PMF for the binomial. So pi to the k times 1 minus pi to the k, where k is either 0 or 1. So that, remember, this is a PMF, not a PDF, so this actually does give us that probability. So we can get the probability of success and the probability of failure. So probability of success is pi, probability of failure is 1 minus pi. So thinking again to our coin flipping, we're going to say heads is a success, tails is a failure. Probability of flipping it and getting tails, aka failing, is 50%. Probability of flipping it and getting heads, aka succeeding, is also 50%. We get new formulas for the expected value and the variance. So first up, we've got the expected value. I've shown you where the calculation comes from, and we see that in the end the expected value is pi. And the variance, again, I've shown you one way to do this calculation. There are others. We find that the variance is pi times 1 minus pi. These are two widely accepted, well-known facts about the Bernoulli distribution, so you don't need to worry too much about being able to prove where these came from or writing out all the math. These are just facts that we know. Two things to note, though. I mentioned that so far we've just done this coin flipping example, and in the coin flipping example, your probability of success and your probability of failure are equal. that's not true in every example. In fact, it's not true in most examples. So the way we account for that in these calculations is each outcome is weighted by its probability. So we see that being done there and there. We're also doing it down here and there. So next up, an example where things aren't equal. In a recent report from the CEO of Smitten Kitten, an online dating app for cats, it was stated that 67% of all cats that use Smitten Kitten find true love. So we're going to call love a success. First thing is we just want to know what's our probability of failure, what's our probability of success. Well, you'll notice that it said 67% of all cats. When you're talking about all of something or everything, you're talking about your population. So 67% is a population parameter. 67% is our pi. So first up, we'll calculate the probability of failure. It's 1 minus the probability of success, so here it's 33%. And our probability of success, that's easy, it's just given to us, it's 67%. Next up, using those two facts, let's calculate the expected value. So I've calculated it the long way here, just again to show you where it came from. So 0 times the probability of 0, so not finding true love times the probability of not finding true love, plus 1 times the probability of 1. So true love times the probability of finding true love, and we get that that is 0.67. So again, we knew that from the start, right? We could have just jumped way down to this is 67%, but I wanted to show you again where it came from. We won't worry about calculating the variance here. Oh, yeah, we will. Never mind. So, variance. This time I did not show you the big formula, just went straight down to the answer. We know the answer is pi times 1 minus pi. So 0.67 times 1 minus 0.67, or 0.2211, so 22%. Now again, remember, in this question, n is equal to 1, so I didn't talk about if there were 10 cats, what happens, or anything like that. I just wanted to know what's the probability of success and failure for one cat. Now, in the previous slides, we were assuming pi was constant. That was one of the assumptions necessary to use the Bernoulli distribution. But in regression, that's often not the case, right? So in logistic regression, we're really focused on the expected value of y given x. So the notation of this, expected value of y given x, we use that conditional notation. So this means it's the probability of success, and that probability depends on an explanatory variable, or a collection of them. Right now we're going to focus on just having one, but you can have many, as we have seen. So for a particular x, which here again I'm using that capital and lowercase notation, x is just some ambiguous thing. Lowercase x is an actual observation of it. In this case, x is one of our covariates or explanatory variables. So here we can rewrite our mean, our mean and variance, or the expected value and variance. Remember, expected value and mean, they are the same thing. So our expected value is now pi sub I, and our variance is pi sub I times 1 minus pi sub I. So that subscript I is just saying we're tracking values of x. So, when x is 5, the expected value is a certain number. When x is 6, the expected value is a certain number. So it's still constant for specific values of x. So if x is 5, the expected value can't be 7 and 10. It has to be one number. But as x varies, the expected value is going to vary as well. So for example, we want to find the expected probability of a successful space shuttle launch. We're not actually going to find it. Your book finds it, so if you look in your book, you'll see them doing this calculation. I'm just going to point out an example of where you would use this. So we saw that, because we already calculated a logistic regression model for this, we saw that the expected probability of a successful space shuttle launch changes depending on the temperature. Some temperatures are really good for this, some are very bad. So we have already seen this, we already calculated the model. And note, we would be violating the constant variance assumption for least squares regression. So this is one of the reasons that we don't do least squares regression here and that we instead do logistic. So up next, the binomial. So as I said, binomial is just a collection of repeated Bernoulli trials, and logistic regression can actually also be used when your response is a count of the number of successes. We're just going to throw this fact out there. We're not going to spend too much time actually doing this. But just as a reminder about the binomial, a count follows a binomial distribution if there are n sub I independent observations at each x sub I. So here we're not just saying there are n observations total, we're saying at each value of x, how many observations did we have? So, when x was 4, how many observations did we have? When x was 6, how many did we have? And so on. We then have a probability of success for each given x. And each response has only 2 outcomes. That's still true, right? Binomial is still zeros and ones, but we're not interested in recording individual zeros and ones now. We're lumping them together and we're recording counts. So at a particular level x, what was the number of successes that we saw? For the binomial distribution is given here. It looks similar to the PMF for the Bernoulli, but now we have that n choose k out front, which if you don't remember what that is, I suggest going back and checking that out. And then now instead of k and 1 minus k in the exponents, we have k and n minus k, because we can have more than one trial. We get a new mean and variance, very similar to the old one. Our mean is n times pi, and our variance is n times pi times 1 minus pi. So we just multiplied each of the old ones by n. So next up, we'll do an example. Suppose in that report, the CEO of Smitten Kitten also noted that the probability of finding true love for a cat that used the app for 14 days, there's our x, is 58%. There's our pi. If 10 cats used the app for 14 days, so maybe we look at our data, we see that's how many cats we had that used it for 14 days, what's the probability that all 10 of them found love? We could calculate this in 2 ways. We could use the binomial PMF. So I've substituted in all the necessary pieces there, and then I could go and calculate that. Or we could use R. So the function that you use is dbinom, and the way it works is this. First, you give it the number of successes that you're looking for. Then you give it the total number of observations that there were. You also give it the probability of success, and then it gives you an answer. And you get to try this type of thing on your own in the homework. So that's the end of Chapter 7, Section 11. And also for this homework, you can use R,